In maintenance hangars around the world, Tokyo, Singapore, London, Dallas, dozens of Boeing 787s sat parked, all without engines. $100 million aircraft, less than 10 years old, grounded because the engines that made them fly were breaking apart from the inside. Airlines operating these Dreamliners had to lease older planes to cover routes while their most modern jets collected dust. The Dreamliner is the best-selling widebody in history, and its Rolls-Royce engines were cracking. The first sign appeared in 2016 when mechanics at All Nippon Airways found microfractures in the high-pressure turbine blades of the Trent 1000. Rolls-Royce attacked the defect, redesigned the blades, put the engines back on the wings, and then a second problem emerged: harmonic vibration fatigue in the intermediate compressor. A different failure mechanism in a different part of the engine. They fixed it again.
Then a third defect emerged, this time inside the engine's hydromechanical fuel control unit. Premature wear in the combining spill valve reduced fuel flow at high power settings, causing thrust shortfalls and forcing yet another round of inspections and redesigns. Every layer of repair revealed the next one. 3 distinct problems, 3 different subsystems, the same engine. Rolls-Royce engineering was trapped in a cycle: fix one defect, discover the next, fix, discover. It was a cascade effect, and both Rolls-Royce and Boeing no longer knew what to do. The success of the 787 has been widely discussed, and we won't go into the reasons again, but the commercial result was devastating for the competition: more than 2,400 orders. Airbus took 3 extra years to bring the A350 to market, 3 years of contracts that went to Boeing while Airbus was still setting up production lines. But all that innovation imposed a cost that didn't appear in the sales brochures. Composites behave differently from aluminum under thermal stress. Electrical systems generate power demands that didn't exist in previous generations. The engine had to deliver more electrical power, operate with tighter thermal tolerances, and adapt to an airframe whose structural characteristics were being tested in service for the first time. Rolls-Royce engineers weren't improving an engine, they were solving dozens of simultaneous problems that the most innovative aircraft in the world was presenting. And this was generating unprecedented wear and internal pressure on the company. Rolls-Royce operates its wide-body engines under a contract called Total Care. The airline doesn't buy the engine, it pays per flight hour. While the engine is in the air, Rolls-Royce earns. It's a model that, in theory, aligns incentives. A reliable engine flies more, everybody wins. The problem is what happens when the engine comes off the wing. When the Trent 1000 started being removed for repair, the hourly revenue went to zero, but the contractual obligation continued. Rolls-Royce bore the costs of maintenance, parts, replacement logistics, zero revenue, maximum expense, at the exact moment the company needed cash most to fund the redesigns. The bill exceeded $3 billion between penalties, repairs, compensation, inspections, operational costs, and more. $3 billion, the equivalent of developing an entire regional aircraft from scratch. Airlines watched the crisis and did the math. The 787 offers 2 engine options: the Trent 1000 from Rolls-Royce and the GE 1B from GE Aerospace. While Rolls-Royce was fixing, GE was selling. New contracts migrated en masse. When the dust settled, GE had captured more than 70% of the Dreamliner backlog. Today, about 34% of flying 787s use Rolls-Royce. For new orders, that number has dropped to 8. In 2023, Rolls-Royce changed leadership. The new CEO, Tufan Ergin-Bilgic, came in and told his own team that the company was a burning platform. The civil engines division was operating in the red. Thousands of employees were let go. Investment programs were cut. The company that dominated the wide-body engine market was fighting not to disappear. Rolls-Royce survived, and the path back ran through something that already existed in-house: running non-stop, without failure, without headlines, on the wings of an aircraft almost nobody was buying. In 2004, when Boeing unveiled the 787 and redesigned the wide-body market, Airbus was consumed by the A380 program. It had no immediate answer. The interim solution was to take the A330, a wide-body that had been flying since the 90s, and equip it with new engines and some structural changes to improve aerodynamics along with a systems upgrade. The A330neo was born as a stopgap measure. Development cost a fraction of what any new aircraft in the category required, less than 10% of the investment behind the 787 or the A350 according to industry estimates. The market treated the result accordingly. About 500 orders, a fifth of what the 787 accumulated. The A330neo entered service as the aircraft nobody took seriously, a band-aid. The engine Rolls-Royce designed for that aircraft, the Trent 7000, surpassed 1 million continuous flight hours in commercial service, 0 in-flight shutdowns, dispatch rate near 100%. Those numbers place the Trent 7000 ahead of GE's GenX and Pratt & Whitney's PW1100G in operational reliability. The most reliable wide-body engine in the world was powering the wide-body nobody wanted. And the reason the Trent 7000 works so well lies in exactly what the market saw as a flaw. The A330neo uses a conservative airframe, aluminum, known geometry, systems tested through decades of operation on the original A330. When Rolls-Royce designed the Trent 7000, the engineers didn't need to split their attention between the engine and a list of structural unknowns imposed by the airframe. There was no unknown thermal behavior from composites. There were no unprecedented electrical demands. The platform was stable, predictable, and already known. The 787 never offered that to the Trent 1000. The radical innovation of the airframe absorbed engineering capacity that should have gone to the engine. The most advanced aircraft in the world created the conditions for the least reliable engine. The most conservative aircraft created the conditions for the most reliable engine. The specific piece that makes the difference is in the high-pressure turbine. The HPT blades operate within a gas flow at temperatures that exceed the melting point of the blade metal itself. What prevents the metal from yielding is an internal cooling system. Cold air channeled through micro-perforations on the blade surface, creating a protective layer between the metal and the heat. In the original Trent 1000, this system couldn't keep up with the real thermal demands of operation. The cooling air was insufficient. The metal suffered cyclic thermal stress on every flight. Thousands of cycles later, the microcracks appeared. In the Trent 7000, Rolls-Royce redesigned the system with 40% more airflow through the blades. The question Rolls-Royce had to answer was whether this technology could be transplanted from one engine to the other. It could, and it was. Rolls-Royce adapted the turbine blade cooling system from the Trent 7000 to the Trent 1000, creating an upgrade package called Trent 1000 XE, extra efficiency. The new blades eliminate the cyclic thermal stress that caused the original microcracks. The engine tolerates sustained operation at high thrust for longer. It performs better in environments with sand and airborne particulates. Time between removal from the wing increases, which means less route disruption, less cost, and the delivery vehicle already existed. TotalCare, the contract that nearly destroyed Rolls-Royce, now serves as the retrofit infrastructure. When an engine enters a shop visit for maintenance, the team removes the entire Trent 1000 core and installs the XE package components. The aircraft leaves with an engine carrying the same cooling technology that made the Trent 7000 the most reliable wide-body engine in operation. New Dreamliners from the factory already come fitted with the Trent 1000 XE as standard. The contract that bled the company now heals the fleet. The FAA approved an increase in maximum takeoff weight for the 787-9 and the 10 variant, the IMTOW. 10,000 extra pounds on the 9, 14,000 on the 10. For the 10, that means roughly 450 additional nautical miles of range, enough to surpass 7,000 nautical miles and cross oceans that were previously out of reach. The more durable engine complements the heavier airframe. The combination brings the 787-10 closer to A350 territory, larger but now not so distant. For 777-200 operators who need to modernize, the math has changed. 25% less fuel than the legacy 777, range to cover most routes, and now an engine that won't take them out of service.
The A330neo received about 500 orders. It won't dominate any route. It won't redefine any market segment. But inside every Dreamliner that leaves an MRO shop with upgraded engines, a piece of the aircraft it defeated travels along. The Band-Aid became the transplant. The best-selling aircraft in history needs the engine from the aircraft almost nobody wanted. And nobody apologized to the A330neo. There's a lesson buried in that irony that goes beyond one engine program. The industry tends to treat innovation and reliability as if they move in the same direction, as if the newer platform, by definition, should also be the more dependable one. The Trent 1000 and Trent 7000 tell a different story. One engine had to mature alongside an airframe still discovering its own limits. The other inherited a platform whose behavior was already fully mapped, down to how it handled turbulence, how its structure aged, how its systems degraded over 100,000 cycles. Confidence, it turns out, isn't just engineered. It's borrowed from decades other people already spent finding the failure points first. Rolls-Royce seems to have absorbed that lesson institutionally. Under Ergenvilgich, the company shifted resources toward what engineers internally call durability-first design, validating cooling systems, materials, and thermal tolerances on proven platforms before ever committing them to something unproven. The Trent XWB, powering the A350, and the newer UltraFan demonstrator program both draw on lessons pulled directly from the Trent 1000 crisis. More conservative margins, more cross-platform testing, less reliance on an airframe behaving exactly as simulated. The financial turnaround followed the technical one. By the middle of the decade, Rolls-Royce's civil aerospace division had returned to profitability, and the company's market value multiplied several times over from its 2023 lows. None of that erases the $3 billion the Trent 1000 crisis cost, or the 70% of Dreamliner backlog that GE captured while Rolls-Royce was still redesigning turbine blades. But it does mean the company that once called itself a burning platform now builds part of its future on an engine nobody wanted to write about.